Thank you very much, Simon and Professor Bay. I really appreciate the opportunity to present to you all and the kind introduction. We're going to cover a few bases today, and I tried to give the initial slide a sense of the high level things that matter. And so climate and performance is really at the heart of everything that RWDI does. We have a number of specialties in our firm, but almost all of them have as a core beginning a connection to the climate or the impact that a project may have on the climate. We strive for high performance engineering, as Simon graciously pointed out. We are very fortunate to be world renowned for our services and our capabilities, which means we have the privilege of having worked on 16 of the 20 tallest buildings in the world, big long span bridges, just about every major sports stadia in North America. So these expertise are highly specialized. These expertise take us all over the world, and I'm excited to share a little bit about all of those with you today. A little bit about me, just to start us off, but I promise not to dwell on this. I am an engineer. I was trained in Canada. I've been in New York for the past 8 years, but my original training is actually mechanical engineering. I did supplemental education in applied mathematics, and then I studied in Europe for my graduate training, which was on environmental performance and climate responsive design over there. And when I went to grad school some 20 years ago, I really felt like Europe was a place that was ahead of the curve in terms of thinking about climate and how to integrate climate into engineering practices of today, and so went and studied there. I'm happy to report that a lot of what I learned in Europe and a lot of what I endeavored to learn in Europe, we now see as major practices in the North American marketplace, but also the rest of the world, including very much emerging markets in parts of Asia Pacific, South America, etc. So a little recap on our agenda. I'll give you a sense of who we are. RWDI is a multifaceted firm. While I condense it all into climate and performance, there's actually quite a few things under our specialist umbrella. But given the background of you all as an audience and your particular training, I thought the wind engineering and supplemental damping is maybe the most important thing for you to get a sense of. But I also wanted to share with you a little forward-looking frontier. So that's why I've got AI tools for early cladding pressures. I've got CFD tools. I'm certainly going to talk about wind tunnels. So if you know RWDI at all, you probably know that we have wind tunnels, and I'll certainly touch on that. But increasingly, we're bringing to bear computational methods to do some of the work or to support some of the work that is conducted with wind tunnels. Simon mentioned a couple times in his intro a climate crisis, and one of the things that is emerging in our practice is an emphasis on embodied carbon. So the industry, AEC as a whole, for the last several decades has really been working on operational carbon. You may know it as energy performance or energy cost reduction, trying to get, whether it's lead points or the evolution of the energy code for buildings, et cetera. But increasingly, there's a lot of emphasis in the market being put on the embodied carbon, and so I'll touch on that a little bit. RWDI. So we strive to create harmony between the built and natural environment, and that is a very rewarding but often difficult challenge. It doesn't have to be structures, although I'll put quite a bit of time today to structures, but here's an example of the Brickell Center in Miami, a relatively new development involving Related and a number of folks out of the New York marketplace. But its endeavor is essentially to be a mall, but a mall that is supported by mixed-use tall tower developments all around it, and a mall that is open to the outside. And so the role of RWDI in a project like this is to try to find, how do we get this to be a usable, occupiable, highly productive retail space while being comfortable, while being protected from certain elements, but getting a sense of the fact that you are in this nice transient space. So highly engineered, all the shades that are in here. You have the moisture protection for overhead rain. You have the opening where you need, or openings, I suppose. You don't see all of them, but this is just one of the openings to air, where we have to understand and be able to control the flow of air through the building to be able to maximize comfort year round. We engineer solutions for a changing climate, and this is a relatively modest building on the west end of downtown Toronto, but the reason I put it into my slide deck is often clientele in the marketplace, be they architects, be they developers, or otherwise owners, they don't quite know how to articulate exactly what they need. They know they need to do something in respect of a changing climate, but they're not totally sure what. This one was a great example because the client came to us at the very beginning and said, I don't know what to ask of you, dear RWDI, but I know I want my design to think about climate. What are its opportunities? What are its challenges? And we're seeing clientele that are willing to ask such things, which is really important. We do see evolution of guidelines, and I'll get into some of the structural stuff here in a minute, but it's not just structure and cladding pressures and things like that. It's also guidelines for the urban realm. So a lot of the world around is putting an emphasis on creating human experiences in the pedestrian realm. We're also seeing human experiences activated at heights we have never seen before. You know, buildings in New York with amenity spaces that are 1,100 feet in the air. That means that you have to have a really good understanding of what the conditions are going to be like up there, and that's a fulsome expression of climate. This particular image is of the city of London in the UK, where we wrote and are now implementing on projects the entire urban design guideline for thermal comfort in the pedestrian realm. High performance projects, this could be one of any number of projects, but this is a tower in Milan, Italy, that went through many iterations of wind tunnel testing in order to find the optimum design, particularly of exposed at the top that act like a bit of a sail for the wind and then impart their load further down into the building. There was also a special effort on this project to have a number of building integrated photovoltaics. And the net result is, I think, a really efficient building that's really sharp, but stands out in the Milan context and is highly optimal in terms of its engineering, not only for energy performance, but in terms of structure and cladding as well. RWDI is best known for our climate lab. So images on the left are two from our large tunnel located in Canada. The top left is Shanghai Tower in its surrounds from the time, doing a smoke visualization analysis. The item below. So we get into this kind of wind tunnel testing outside of the built environment. This is a power installation, utility grade, utility scale solar trackers that are being tested for their positioning in the wind. What kind of loads will they experience, including how do you find the safest place possible if a storm is coming through? Where is the right place to move the panels into so that you don't get failure or fatigue on the tracker structure, etc. On the far right side of the screen is another tool in our belt. This is the water flume. The water flume is essentially similar to the wind tunnel, but the working fluid is water as opposed to air. Water has the benefit of being able to drop in a particulate to the flow of the stream across whatever it is that we have modeled, so that you can simulate the aggregation, the accumulation of snow or sand or other things that would be borne on the wind as they may accumulate around structures. And so we use that tool in addition to a number of different analytical methods to be able to support a good understanding of how these sorts of depositions may occur in and around buildings. Increasingly, we are leveraging computational tools. We have been active in things like computational fluid dynamics for decades. It has not gotten to the point now where it replaces the tunnel, but it's very complementary to the tunnel, and I'll show you what that looks like as we go through the presentation. Different areas of expertise under RWDI, highly sensitive to topography. This is actually emissions pollutant dispersion being modeled at a beyond the microclimate scale. This is up at probably around 10K by 10K. So we're 50 years old. We're about 800 specialists around the world. We have 30 offices divided between 3 primary regions. The regions that we operate look like this. The darker shade on the world map indicates a country where we have done work. And it actually gets lost a little bit, but we have the one that's hardest to get on your continental bingo card, which is Antarctica. We've done a number of research stations there looking at wind and snow accumulation and drift and so forth. So we have offices in Canada, the US, the UK, and into Asia Pacific. The wind tunnels, or the climate labs, are located in Guelph, Ontario, Canada. One of them is, there's 3 of them actually at that facility, plus the water flume. So there's 4 major instruments in Guelph, Ontario. That's just west of Toronto. We have another facility with wind tunnel to the northwest of the city of London. That's in Milton Keynes. And then we have 1 tunnel, and we're building another, perhaps 2, in Trivandrum in the south of India. We are working every day of the week all over the world. To give you a sense of scale of project work that RWDI does in our areas of specialty, we do thousands of projects per year. So, but our scope is smaller, narrower as specialists than, say, the architectural design or the structural design. We are called upon for our specialties at a variety of places throughout the project, but it means we do a very high volume of projects throughout the year. To give you a sense of the disciplines that we have under our belt, and I will not be reading all of these, the presentation today is not hoping to cover all of these, but we are a firm of specialties. And that is exactly where we want to play. We do not want to be in the main design disciplines. These are all of our clients. So we don't want to be cutting their grass. We want to be specialists that help in between all of these things. What binds them all together is there's a heavy reliance on climate expertise. There's a lot that focuses on human expectations, so human-centric solutions. And we're privileged that most of the projects we work on around the world have very high performance expectations, whether that's structural acceleration or energy. Performance metrics come in all shapes and sizes, but maximizing performance is a really key element. So now a wind engineering overview, and forgive me if you've each studied a little bit of wind engineering in your practice. I may cover some stuff that you're already intimately familiar with, but how do wind and structures interact? And so this is an image where the motion of the building is actually magnified by a factor of about 20, but it is really important to understand these buildings that we build, they do move. They do experience wind loading. Yes, there's dead loading. Yes, there's certainly seismic loading, but often, and for many projects around the world, wind loading is one of the critical loading parameters, and it is important to understand the way that it interacts with a structure and the way that the structure will respond to that loading, including that buildings move. Now, the building code, I'm specifically referring to North American codes here, but it's pretty well true the world over. The building code has guidance for structural engineers on how to assess wind loading or cladding pressures, either of them. It is a relatively generic approach. It is a little bit conservative, and it's important to understand the context that it is most applicable. It is most applicable in the along wind direction. So wind coming from the left side of the screen, moving towards the right against my structure here in plan view. And you can imagine a code that says it pushes on it and then the building responds. So you get this along wind response. But for many structures, it is actually the across wind that is the governing load. It is the largest load at the appropriate frequency, and it is the thing that will be most impactful for design. Now, the thing on the bottom here is just a general rule of thumb. I'll show you some other rules of thumb later, but it is most typical that the across wind vibration, the across wind motion and forces are stronger at heights greater than 120 meters. It can be true that that is lower it can be true that it ends up higher. It depends on a whole range of factors like the surrounds, the particular climate that you're looking at, the aspect ratio of your particular building. I mean, we have done plenty of work on a crosswind dominated buildings that are nowhere near 120 meters tall. But there is a role, I think, for the practicing structural engineer to be thinking about, hey, how much vulnerability do I have here? And does the code give me a good representation of what my building will actually experience? To try and understand what it is that is driving that crosswind response. Here is wind coming out of the left. This is a large eddy simulation, CFD, just for the purposes of understanding the phenomena that is at play. Wind pressure builds on the front side. You get some positive pressure and displacement in the along wind direction. But what emerges is a vortex shedding phenomena. And so as I play the video, you can see the alternating eddies that come off as vortices. What that manifests on, to the building is actually a stronger than a long wind, a crosswind response. So the building is being pulled and pushed up and down on this screen more than it is being pulled and pushed in the left to right. To give you a sense of what that looks like when we do an aeroelastic model of it, this is a design iteration of the spire that sits on top of the Freedom Tower here in New York. And this was an earlier design iteration, and you can see our tunnels are a little dated here. This is one of our older facilities. The newer ones are a little pretty, but this is a really really good video, even if the tunnel looks a little dated. So you get a sense of, I don't know if the audio came through, it just sounded like a wind tunnel. But if it did come through, then that's what it sounded like. I mean, that was just a physical manifestation in a non-rigid, so aeroelastic model, showing exactly that crosswind response as measured in the tunnel. So why would we want to conduct wind tunnel tests in order to study these loads? Well, wind loads are notoriously difficult to predict. I mean, you think about the compass, there's 360 degrees of potential direction. There's turbulence in the air naturally, so wind passing by is not a pure linear function. You have boundary layer conditions, including the roughness, i.e. the other buildings that might be around your building, or topography changes, etc. The buildings that we design now in the world are complex in terms of their building shape. There are some, rectilinear plinths out there, but there's also a lot of bends and curves and shapes and sails and all sorts of things. Interference effects from immediately surrounding buildings. So if you think back to that image I showed with the vortex shedding, if you are the building that is downwind of said building, you're experiencing the effect of your neighbor. So those are very important. Complexity of upwind terrain, the terrain conditions are not so complicated somewhere like New York, but if you go to Hong Kong, that's a different story. Complexity of dynamic behavior under wind load action, that's a lot about the actual properties of the design and the crosswind response that I showed. There is a lot of inherent conservatism to cover all this risk. The code is inherently relatively conservative. And so there is an optimization opportunity here, in addition to a risk management opportunity here. So buildings that would experience loads that are not covered by code and would be larger than what code would tell you, well, that is risk management. On the other side is the opportunity to have wind load that is more optimized to your project, therefore is below what the code might otherwise conservatively tell you to do. The world is now has many non-standard, non-compliant with code. Don't get me wrong; these buildings are absolutely compliant with code. They're in Mississauga. They're under construction now. But what this slide is intended to say is that they're not an easy or natural fit to the way that the code would tell you to assess wind loading. And so they're great candidates for having really optimal study in the wind tunnel. We see all sorts of shapes and sizes. We have bridge interconnections. We have, very squat type buildings, a lot of pairing of towers coming these days, which may or may not be a singular structure. They can sometimes be completely isolated from one another, although they look like they're together. But these things can interact or not. In the case of the one on the bottom right, that absolutely will interact with one another. And so you're really working on a problem with three independent bodies with connection, and their behavior in the wind can be as complicated as you might guess it to be. All sorts of different shapes. These are again a few from some of our older tunnel facilities, but we've been privileged to work on some really incredible towers, some of which have been built, certainly Burj Khalifa. This one I can tell a little story on, but some of the others, Petronas Towers for sure, but and this guy is Atlantis. But all sorts of stuff comes through our tunnels. Some of it gets built, some of it doesn't. Some of it goes back to the design drawing board. Burj Khalifa is a fascinating story, and if you were on a little early, Simon and I were talking about Bill Baker being one of the architects involved in this, but really leveraging the output of a wind tunnel to inform the shape and orientation of the tower. So all of these little setbacks that you see that are actually built on the tower, these are mechanisms, in addition to making for interesting architecture, they are mechanisms to have different sectionality in the way that the wind interacts with that facade. You're breaking up into sections the aerodynamic profile of that project, such that you have a different frequency of vortex shedding as the wind encounters, depending on which section of the tower you're looking at. So you're kind of confusing the wind, as opposed to something like 432 Park Avenue here in New York, where you have a rectilinear plinth that has essentially the same cross section, regardless of where you are on the height of the tower. So there's serious aerodynamic advantage to the shape of this. Now, in addition to that, it has a tripod podium, and we were able to turn the tower from its original design to be the optimal direction relative to the wind. So wind tunnel studies we do for all sorts of buildings. We also touch on pedestrian level wind. I'll come back to that a little bit more, but often we're doing structural wind load studies for buildings, particularly tall ones or slender ones. We're doing them a lot on long span roofs. So these are other areas where we know that code will often be challenging. Complex shapes. This is increasingly the case in the world, that architects are coming up with some really interesting shapes and sizes of buildings, and cutaways here and overhangs there, and amenity spaces high up in the air. So there's a lot of interesting shape stuff going on in the world, and so that means the demand on having really dialed in structural loads and cladding pressures is becoming ever more important. Aeroelastic we don't do all the time, so a lot of our work is based in rigid models, but when you have a highly dynamic building or particular amenity or feature of a building, like what I showed you on the spire for the Freedom Tower, we will actually build aeroelastic models. So these are models that are designed to move, but they are designed from a model scale and a model deployment to have the characteristics at scale of the structure. So things like stiffness and mass and so forth. We try to emulate the characteristics in model scale that are at design, and then test on that basis. All of our bridges, for instance, we do a lot of cable bridges, suspension bridges, but also some of the more rigid ones, but we will build aeroelastic models given the potential for movement. The way that the wind tunnel works. So one of the primary instruments that goes in the tunnel are these flexures. So a sway flexure and a torsion flexure. Essentially, these are instruments that will measure the amount of force being imparted to the wind, and they measure it over time so that you get the fluctuations and the movement and so forth. So here is the flexure being shown in a model of Burj Khalifa, so you can actually see the instrument. Normally it's embedded inside the structure, so you don't see it when it's in the wind tunnel, but that's what's there doing the the measurement. So high frequency force balance, and we're able to pick up like millions of data points over the course of a wind tunnel test in order to do the calculations later. Another way to do this, so this is a method you can see on this building, there's all kinds of little pressure taps, all these little spots, and then these are all the tubes where the pressure tap leads back to a data collection system. And so all of these little pressure taps are measuring at the point in time when you spin around the wind tunnel compass, what is the pressure at that specific place in order to get structural load, sort of a two birds with one stone approach. So in addition to the cladding pressures, you're getting what is the overall structural forces, moments, etc. And you do that through an integration approach. So essentially calculating the total force, the aggregate of force exerted as a moment or otherwise, but aggregated overall that you see from the various little point centers that derive pressure. Aeroelastic model testing, sometimes we do very large aeroelastic models where we're capturing that stiffness, capturing that mode shape at model scale, and then testing as such. The way that the workflow usually goes, so an architect will send us a 3D model. It usually has way more than we need for our work included in the model, but our job is to clean that model and get it ready to go into our model fabrication, where we build the physical model, we instrument the physical model, we place that model in all of its surrounds so that we can put it in the wind tunnel and do the tests. Other key parameters, you'll see it is very important to have the building in its context, in its surrounds. But then as you look further up the field, we actually start to introduce obstructions and roughness to the surface that the wind travels down in order to get the right profile of wind. So if you think of this as kind of a U shape, this is the wind velocity profile. We need to have the wind tunnel mimic that which is not only the buildings that are around whatever our subject is, but perhaps the right characteristics of the lower parts of the boundary layer well in advance of the actual structure itself. And so we have these little fins that are in the tunnel, and we can calibrate those fins up and down to get the right wind profile for the project. That would be different if you're talking about, let's say, I'm down in Financial District in Manhattan, so if I was any of the towers that are directly on the water, for the right wind direction on the test, I will want a fairly smooth surface leading up. If I am deep into Midtown, but I only have a portion of Midtown on my horizon, I will want some additional roughness to represent, say, the wind direction coming down from Central Park through all of the super tall towers that are there, et cetera, even if my project is down, I don't know, say 34th Street or something like that. So this is a model being loaded into our newest and largest wind tunnel. This is a 24-foot tunnel. And the disc that you can see is fabricated beforehand. Sometimes it'll have buildings, sometimes we're studying something in isolation. But we're loading it into the wind tunnel from below. And then the fans or the wind will originate from the end of the screen. And then we'll be able to spin the disc as we look at all the different angles of study. So a summary of the steps involved in a wind tunnel test: it's assessing the surrounding terrain, understanding what the profile should look like. It's evaluating the local wind climate. It matters what directions the wind comes from and how often, in addition to how strong that wind is likely to be. We build physical models, sometimes aeroelastic, sometimes rigid, of the specific building itself. We test it in the wind tunnel, going all the way around every time. We record and process all of that data, and the raw data that comes out of this is massive, massive data files, but we have to compute them all down into things that are tangible and usable by the teams that we're working with. And we have to be able to communicate what it is that we do. There are a lot of structural professionals developers, architects, etc., who are familiar with wind tunnels and wind tunnel work, but there's quite a few who are not. And they have to learn how to work with the material that we provide them. And we have an obligation to provide it in a friendly format that they will know what to do with it. Typical parameters, so we certainly talk about forces and moments and things like that, but we also increasingly talk about serviceability criteria. And so that means, what is it that we are expecting to provide for the building occupants? Knowing that these buildings will move, what is an acceptable amount of movement and how does it express? The most commonly used motion comfort criteria, serviceability criteria, are measured in milliges for residential, hotel, and office types. Increasingly, there is an emphasis not only on the 10-year event, but to have a more frequent threshold. So one of the sets of criteria that we recommend is a 1-year event that's consistent with ATC Design Guide 3, but looking not only at the 10-year serviceability, but increasingly at the 1-year. And in some projects, we actually look at a more frequent parameter than even 1 year. Factors that affect the wind-induced response, certainly the wind speed and direction, the shape, all those things. To do our work, we accept from the structural engineer what is the stiffness of the tower, what is its mass, mass distribution, the damping, mode shapes, etc. And we use those to provide feedback to do our analysis and to provide feedback. If you want to shape your building aerodynamically, what are some of the features that you might do to try to drive down wind loads or to mitigate serviceability issues? So physically, you can do things like slotted corners, chamfered notches, tapering towards the top, which Burj Khalifa had some of that in it, but it also had the breaking up of the nature of the shape. Enhanced surface roughness, porosity. So 432 Park Avenue has the benefit of wind pass-through floors. And that again is like breaking up the sections that will experience the vortex shedding. Added porosity, sculptured building tops, etc. Now, to do aerodynamic shaping well, usually these have to be significant motions. Little things like little fins that are primarily there for solar shading, they aren't going to do a whole lot in terms of the building structural load itself. Usually when you're using these sorts of moves architecturally, they need to be significant in terms of their proportional size and scale. But they can be impactful, and there's a lot of work that goes on in terms of chasing for the most optimal solutions. Here's an example, One Bloor West, new very tall tower in Toronto. The original concept design was fairly rectilinear. I mean, there were a couple of slots in here that weren't going to do much beneficial, but working with us, we were able to evolve that design through multiple iterations, each having a different aerodynamic characteristic that was going to help with the reductions in the load. If we measure that in terms of the serviceability criteria, we started with 33 milligs, option 1, 2, and 3, without changing any of the other structural properties. This is just as a function of the aerodynamics. We were able to decrease the serviceability. Ultimately, this is a project that knew early on that it was going to have supplemental damping involved. Originally conceived as a TMD, a tuned mass damper. And if you compare the size of the damper that would be required depending on the serviceability options, the architectural shaping, that damper would have had to be a little over 1,000 tons, 700 tons, and then in the final design only 600 tons, which actually shows up as substantial savings when you go from that size down to that size. So the final integrated design is closest to option number 3. A little more on supplemental damping, and I'll be relatively brief in this part, but tall buildings keep getting taller, they keep getting skinnier. Their natural periods of vibration are getting longer. They have low inherent structural damping ratios. Aerodynamics are becoming more and more important, and they have to get into the right combination of motion and drift targets and serviceability criteria. may be inadequate for these structures. You need to be thinking about the long-term performance of them, and so that's part of why we have been working with not only the 10-year that has been around for a little while, but also the more recent 1-year. To give you a sense of adoption of these things in the design of towers, so just in New York City alone, let alone the rest of the world, up until 2005, there were 4 supplemental damping projects done on buildings in New York, and since that year, over the course of 20 years longer, there have been 37. So if you're looking from Central Park south, you can see, and this isn't all of them, there are more than just that are here, but many of the tall towers built in New York now have a supplemental damping system. One of the first that we did is Taipei 101. So this is a swinging pendulum damper. Essentially, the mass is the big ball. It is inherently unstable. It is suspended by cables above, but then you've got some energy dissipation, viscous dampers around the bottom, and it is very active. So when a typhoon comes through, it absolutely is working in opposite direction to the movement of the structure, helping to dissipate and control the degree of motion and therefore the acceleration that is apparent while you're in the building. In the case of Taipei 101 and Shanghai Tower and a couple of others, these can also have a fantastic additional feature, which is they're a building amenity. People pay to go see the damper, and now they're looking at the pendulum swinging. Some days it moves very little, some days it moves more, depends how windy it is, but it is also an economic opportunity for the project. A whole multitude of different types of designs of these things. A very unique damper inside of 432 Park Avenue, or pair of dampers actually. But the dynamics on that motion gets very complicated. There's a bit of a rendering of it here. But as the building moves, and even the earlier slides I was showing with like the along wind and the across wind, well, buildings actually start to move in more of a combination mode, and so it's not just that it is always linear, front and back or left and right. They do start to rotate. So that was supplemental damping, and these are very much like the traditional areas of RWDI practice. I wanted to give you a little sense of some of the innovation that we're pursuing, particularly in the realm of the computational. So everything up until now is established engineering, highly coupled to the physical test, but there is an emerging role for rapid guidance on these things. And that's where the computational tools are finding their most utility at the beginning. So we get asked questions by clients all the time, like, can I get early insights on pedestrian wind, comfort cladding, structural wind load? And the project is only up in the concept design phase. The pace of design at that early stage, the client's willingness to pay for detailed, wind engineering studies is not great. They're looking for quick guidance at that earlier stage. And so this area, this early design area, is really where those computational tools are finding their greatest utility early on. So I'll touch very briefly on some tools that we have developed for cladding pressures, for structural load, for outdoor comfort, and a little bit on decarbonization. Give you a sense of the range of technologies that we work with and that are present in the marketplace. Certainly computational fluid dynamics. This is RAN CFD, so Reynolds average Navier-Stokes CFD, essentially averaging out a lot of the turbulence in the model in order to decrease the amount of compute that is required. In the middle, you have a transient CFD, LES, large eddy simulation CFD, so higher fidelity work that we do, also a CFD engine. So CFD is not CFD is not CFD. It's a kind of umbrella term for many different approaches of a mesh with the approach to solving Navier-Stokes equations, but these are two primary methods, and they have different strengths and weaknesses. Increasingly, there are AI models that can do this, and we have been training our own machine learning models based on data sets. I'll show you that in a sec, but what is absolutely critical when you're in our line of engineering and work is all these tools have different strengths and weaknesses. We need to be able to truth them back to some measure but which we can calibrate against. And so for us, that's often the wind tunnel, for which we have correlation to the real world. So this plot is actually showing in plan view a RAN CFD, an LES CFD, and an AI prediction of wind that is moving from the top of the page to the bottom of the page. The redder colors are acceleration, so that's higher wind speeds. The bluer colors are areas of stagnation. But we're comparing this technology, these three computational technologies, against the little dots, which are wind velocities that we would measure in the wind tunnel. And so for us, it is absolutely critical to understand strengths and weaknesses of these technologies in order to use them in our practice, knowing that the wind tunnel remains the gold standard of how you assess this sort of phenomena. We trained that machine learning model based on our wind tunnel data, also through some of our computational fluid dynamics results. But here is a plan view of an AI model output of pedestrian wind. So it's wind in the ground plane, but where you have corner acceleration of wind moving from left to right coming around that building. Same thing, a little channeling back there, areas of stagnation in blue, quiet wind speeds. But this AI-based prediction is actually quite good. It looks like CFD. If you didn't know it was AI, you'd probably guess it was CFD. It doesn't look like a wind tunnel test, but it is staggering how quickly we've been able to build this engine over the course of time and leverage the science that's going on there in order to produce results. In application, this is early design for cladding pressure, so a rapid AI simulation where we are predicting pressure coefficients, positive, negative, means on the facade to inform the facade design. It is inclusive of all the same things that you would have in a wind tunnel test, so the project-specific meteorological data and all the surrounds. We do multiple return periods, 50 years, whatever the particular thing is that we're looking for those pressures, and we can map out results in a 3D viewer. So really useful for clients trying to understand like the benefit or challenges of various shapes of an initial tower. Where am I going to have hotspots? How big a magnitude of a pressure hotspot might I have? But there are some limitations to it. We need to be communicative to our clients about there's some trade-off here between the accuracy of an AI model relative to a wind tunnel. They're not the same. You cannot use these for final design and engineering. They're useful for early design guidance only. They're not terribly sensitive to smaller, more nuanced moves. Like if you move the tower by 5 degrees, it probably isn't going to produce a substantially different result, where you may have a stronger result in a wind tunnel. So for future, we're thrilled about where this technology is and where it's going. We see it as useful in early design now, but it is not a replacement for a wind tunnel. We will continue to expand the training data sets. I mean, we have thousands of projects in here, but as I said, we do thousands of projects per year, and we've been running wind tunnels for 40 years. So we've got a lot of data to go mine the lake and continue to refine these tools. This is a validation exercise. So there's a machine learning AI pressure estimation mapping on the left. There's the wind tunnel test, and then this is an R-squared correlation on the maximum CP. And you can see it's quite good, but they're not the same. You get divergence in the scatter plot from the ML prediction on the right versus the wind tunnel measurement. But an R-squared of 0.9, that's still pretty good. This is another very similar exercise, but measuring a corner tap. What does that specific spot on the building, when I go around the compass, when I go through all 360 degrees of wind direction, and I plot, what is that corner tap reading on the wind tunnel versus what is it reading on the AI engine? And you see the right patterns. So the AI is doing pretty darn well. It's not exactly the same, and you need to understand the differences, but it is pretty good. There's min pressures, max pressures, and mean pressures at that very one location. Now we have to do that across the entire thing, every tap. When we do this, we seldom look at one point alone on a building. In terms of what do our clients look to see or receive from us, they're looking for pressure maps with the appropriate return interval, and so we will produce whether computational or wind tunnel, we will produce these pressure maps of different PSF zones on the facade. So that was cladding pressure. Now I move into structural wind loading. So we have often the question from a client, hey, do you think RWDI, do you think there's going to be value in a wind tunnel test on this project? And we know from surveys of the projects we've done in the past that there is often an opportunity to be below what the conservative code would tell you. But it's very difficult to hang your hat on it early in the project. And so here's a selection of projects of varying heights out of London in the UK, where the dark blue, and this is just measuring one variable, but peak overturning moment, wind tunnel study on this project number 1 at 72 meters of height, substantially below what would have been calculated via a code-based method. Well, now with a computational tool that is a little lighter, a little faster, we're able to give confidence to clients to say, hey, if we measure this quickly computationally and tell you this is a good candidate for a wind tunnel test to generate savings, then that's a real advantage in terms of optimizing the project for a client. The method uses LES, large eddy simulation, CFD, and then it includes all the other characteristics that you would normally find in a wind tunnel. It is particularly useful for measuring initial shapes. So this is tower shaping with early design, C1 config, C2, C3, C4, being able to quickly give guidance back to a project team about what those high-level characteristics are. There are limitations here as well. It cannot be a substitute for a wind tunnel test. You still need a wind tunnel test for final design, final engineering, etc. We continue to refine these models. We continue to work on how to integrate them into the workflow, but they have limitations in terms of their sensitivity, etc. But in pairing, they can be very useful. And so here is a project where we did a combination of LES computational stuff followed by a wind tunnel test. And just as a proxy for how much load reduction, here is a 90-degree angle corner. So these are all again in plan view. And you can measure the size of the wake. That has a rough correlation to the amount of load that will be experienced in terms of crosswind loading on the project. And then you can see the design solution that was chosen that has these rounded corners. And you can immediately tell just by looking at the computational wakes, this building is far more aerodynamic than that one. And so that optimization then plays out in the wind tunnel, and it affects all sorts of things to do with the structural design response, including, like back on my one Bloor example, the size of the tune mass damper that went into the top of the tower. We do a lot of work to validate our computational work, and this is absolutely critical. You have to know what you're doing with CFD and computational works. You have to know the strengths and weaknesses because there are many. But it's the same criteria that we're evaluating against, so forces, moments, serviceability criteria, including accelerations. Increasingly, embodied carbon is a critical variable. So for 20 plus years in North America, we've been tackling the operational carbon, i.e. the energy use, but increasingly projects are being required to think hard about the embodied carbon that is associated with the design and construction of the project. And it can be a substantial portion of the total carbon budget affiliated with the project. Now, the traditional way that design teams will look to tackle embodied carbon is things like low global warming potential and refrigerants. They'll look at material substitutions, so substitutions for Portland cement or low carbon embodied carbon steels, etc. One of the things that I think really needs some attention is there is a lot of opportunity to reduce embodied carbon by having a structural design response that is optimized to the wind load. And that goes back to the graph that I was showing, wind loads through the wind tunnel that were below what the code would have otherwise told you. But those are real savings, as in, if you had just designed building according to code, you might have had double the amount of loading criteria from a wind perspective. And that manifests as concrete and steel and rebar and all the things that represent embodied carbon. So we've developed a simple method to be able to estimate that. So we get one design, we compare it to another, usually the code-based design, and then we're able to quantify what is the reduction, rough order of magnitude in embodied carbon associated with that design alternate versus its code comparator. If you do that from a variety of project scales, Shanghai Tower on the left, the combination of the amount of shape, the twist in the tower, and its orientation yielded substantial material cost savings. I mean, it's a big, expensive tower, so $60 million is a lot, but it's also a big, expensive project. But it is a substantial amount of embodied CO2 savings, in this case, 20,000 metric tons. The same pattern plays out, but it scales a little bit in high-rise and mid-rise buildings. And this is just embodied carbon reduction associated with having the optimal loads, like the project-specific loads. Outdoor comfort as a bit of an extra piece here. So while we're doing a lot of our wind engineering work for structure and cladding, we're also looking at pedestrian wind thermal comfort and increasingly heat islands. So the shape of a building can have an enormous impact on how you will feel and experience the outdoor realm of the space. And we see a lot of buildings now with activated exterior amenities. So there's a lot of simulation wind tunnel test work that goes into this. We're combining temperature, humidity, full met data, full wind flow, sun shadow, and what we're deriving at is total comfort. We do this in a couple of different flavors. We do AI, we do RAN CFD, and we do LES CFD. Typically, the AI is best for like the really quick estimation of thermal comfort or pedestrian level wind. And then when you have potential for safety concerns, we're almost always going up into the large eddy simulation CFD type. But there's a few spots around the world where the RANs is required for regulatory purposes. So that brings me to the end of the presentation, and I thank you very much for your time and attention. I'd be happy to take questions. I think we have perhaps it's 20 minutes on the agenda, and can certainly do that. But maybe to conclude, we're a very specialized firm. We do really, I think, fun and interesting stuff. I hope I've given you a sense of that today. We're very privileged in that the handprint of our work, like the number of projects around the world that we touch, is very, very large, and considerably larger than the size of our organization when we measure our own footprint. So it's a point of pride for us, and something we enjoy very much.